I'm in the middle of redrawing the diagram for cubic surfaces and characteristics 0. I'm drawing it upside down because I realized yesterday that all of the interesting stuff at the very bottom of the board, and I think a lot of people couldn't see it. So I'm drawing it upside down so that you can, just a reminder so that you have some context for what I'm talking about today. So, let me finish the diagram. Automorphisms and cubic surfaces characteristics 2 and 2. So we have so recall last time somehow I justified all of these segments here. So there's exactly one automorphism with the order what about characteristic 3? So let me just recall just what we said last time. Here, so this is the same story in the characteristic greater than 5. Exactly the same automorphism. In characteristic 5, we still see the surface that has this automorphism group, but it's not smooth. In characteristic 3, last time I told you that there's an analog of symmetric. Yeah, I think it's, that should be easy. So there's some characteristics. There's a different model. Nevertheless, you have this kind of replacement. So the Sylvester form in characteristic 3, where you have you can always write down the cubic in the following way. A general cubic has the following form: plus omega,
where omega is some fixed form. It's symmetric functions in 4 variables. Yeah, I could write it down, but I don't think that it's particularly illuminating. And so the idea is as you change these VIs, you can realize any of these automorphism groups over here. In fact, you can say quite a lot more. It seems like this is in the situation of characteristic 3. So there's a theorem. Now they certainly were not thinking about this cubic surfaces when they were writing these papers. They were interested in something called pre-homogeneous vector spaces. But so Chen Ji and Cohen and Wales basically made the following observation. So if you take V to be the span of the cubes in the symmetric polynomials in 4 variables, okay, then there's this interesting fact that in characteristic 3, V is a GL4 invariant subspace. In other words, if you act by a matrix, because you're in characteristic 3, when you replace this with a linear combination, you replace x1 with some combination x1 to x4, because you're in characteristic 3, you just end up still in the cubes. So this is only true in characteristic 3, and it's kind of unusual. And so there's an obvious thing you can do is you can quotient out by this subspace. And this is what's called a pre-homogeneous vector space. So what's a pre-homogeneous vector space? In other words, there's a GL4 action on this vector space with a dense open orbit. And you can sort of convince yourself that this is reasonable.
So the point
yes.
is, it's not really the span of the cubes, it's the cubes themselves, yes?
The span of the cubes.
Span.
Span. The vector space span.
So the vector space.
It's a vector space.
Those 4 points.
Not 4 points, yeah. It's, so
Okay, so but it's also
anything that looks like this.
it was just cubes of linear forms.
Yes, it's equivalent to cubes of linear forms because we're in characteristic 3. In other characteristics, you would not have this, you multiply this by a matrix, you're going to get some mess.
Yes, sure.
Yeah. So it's very special that this happens in characteristic 3. This is a pre-homogeneous vector space with an action of GL4 and it has a dense open orbit. And what's interesting about pre-homogeneous vector spaces is that they've been classified in I think all characteristics now, and this is sort of this is a particularly special case that only shows up in characteristic 3. And there's kind of an interesting thing that's special about cubic surfaces. And so it has a dense open orbit. And moreover, in fact, it has exactly 11 orbits. And we know what they are. And Cohen and Wales work out their stabilizers. So in other words, there's a list of 11 things you can write down. And you can write down any cubic form as something looks like this plus one of these 11 forms. Okay, so which is a very strong result, and you wouldn't expect this type of thing in any characteristic other than 3. And moreover, if you do some work, you can actually extract the entire classification of all actions on smooth cubic surfaces just by looking at the stabilizers, which Cohen and Wales actually figure out. So in a sense, the classification of automorphisms of cubic surfaces in characteristic 3 was sort of already done by Cohen and Wales, although they weren't interested in this, and so you have to do some work to extract it from their work. But anyway, this is an interesting fact that only applies in characteristic 3. Okay. But I still wanted to talk about what happens. So I claim that the picture is exactly the same for all these symmetric groups. Or not exactly the same. I mean, you have this kind of thing. So you still have all these groups. So what happens to the cyclic surfaces? So the cyclic surfaces, as I said before, these are triple Galois covers of P2 by definition. Okay. And then so the question is, well, that's a problem. You can't write down x naught cubed is equal to some cubic form in characteristic 3 and expect it to be smooth. In fact, it's never smooth. But you still have what I'll call you still have cyclic surfaces. So these are the cyclic cubic surfaces in characteristic 3, and I'll give you a normal form. This is not what Cohen and Wales write down. I like this one for a variety. I'm not going to talk too much about where this came from, but this happens to be the general form for a cyclic surface in characteristic 3. I just wanted to write it down. Notice how this sort of does fit into the previous situation. There's some parameter, lambda. This is analogous to the lambda that I used for the cyclic surfaces yesterday. So if you remove this and you remove that, then you have the normal form that shows up in Cohen and Wales' classification, but you can actually reduce it further and you don't have to consider all cubes. Okay. So what is the deck transformation? So in other words, if you have a triple cover, and it's Galois, how does the Galois group act? And it acts by taking x naught to x naught plus x3. Okay. So you can't multiply it by a cube root of unity like we did yesterday because they don't exist. Okay. But instead, since we're in characteristic 3, you realize that this is a cyclic automorphism of order 3. Okay. And you can check pretty easily by hand that this preserves that equation. So immediately the question becomes, okay, so we have this center, right? This is that's what this was in the case of characteristic 0. So what about the additional stuff? There's no elliptic curve here. Okay. So it turns out the ramification locus is where x3 is equal to 0. So it's, if you intersect this with the plane x3 equals 0, and you find that you get a cuspidal cubic rather than an elliptic curve as lambda varies. Okay. So this is a cuspidal cubic. Okay. But nonetheless, you get exactly the same automorphism. You get the same automorphisms acting in the general case. So this is not obvious, and if you there's not a very nice presentation for them. You write them down as an upper triangular matrix, and it's a bit of a mess, but you can do it. So this has the same automorphism groups for a general lambda. For a general lambda, the automorphisms that extend to the whole thing are still the same group. You still get the same group. And something that I would like to know the answer of, and we're trying to figure out, is whether or not this actually lifts to characteristic 0, the whole group, and we don't know. It's the only one. It's the only one for the cyclic cubic surfaces that we don't know whether or not this lifts. Okay.
Sorry.
Yeah.
But you know that in characteristic 0 this group is present, yes?
Yes. We know in characteristic 0 that this group is present, and we know that it's present in characteristic 3, but we're not sure if there's a deformation from characteristic 3 to characteristic 0 such that you can realize this group. So that's, I mean, it's a much weaker question than does this group exist. But
Do
it
you
does.
know the explicit equation of cubic realizes?
This group? Yes, this one. And I can explicitly write down, using matrices, what this looks like in characteristic 3.
So your point is that when you write this down in characteristic 0, the same equation?
If you write down the same equation, then it's just a different cubic surface. So you have to find some nice, if you change the way that you write down your equation, you might be able to write this down in characteristic 0 in such a way that things descend. It's not clear. So that's an open question that I think we're close to answering, but I don't know the answer. So yeah, it's just a natural question, and I don't know the answer. So this is only the general one. So what about these two specializations? So recall, in characteristic 0, with an elliptic curve, you have sort of two special elliptic curves that have additional automorphisms. Right? So rather than just the group automorphism, you have a group automorphism that acts by of order 4, or you might have a group automorphism that acts by order 6. Okay? But in characteristic 3, that analogy sort of breaks down, and you end up with only one special elliptic curve, and this isn't really even an elliptic curve anymore. So what happens to these additional guys? Well, the Fermat, recall this was just the sum of cubes. This disappears in characteristic 3 for the same reason that this one disappeared in characteristic 5. This is singular. In fact, it's a tripled line, or a tripled hyperbola, excuse me. This, on the other hand, this guy stays around. However, it has more automorphisms, and these guys, so it ends up acquiring an automorphism of order 8, and so both of these families are the same in characteristic 3. So if you set lambda equal to 0, you get the analog of this group, and then you find that actually there's also an automorphism of order 8 on this. And so there's exactly one surface where both of these act in characteristic 3. So somehow the two different surfaces over other characteristics come together in characteristic 3. But otherwise, the actual automorphisms look very similar in characteristic 3. So it's somewhat of a surprise. We expected, or I think a lot of people would have expected this to look very different in characteristic 3, but it's very similar. Okay. All right, so now I want to talk about characteristic 2. And here, this diagram looks very different. So I'm going to write down the automorphisms next to it, and to give you a sense about what happens. And I'll explain what these automorphisms, how these automorphism groups are related to the characteristic zero case. All right. Okay, so I'm going to use the same sort of notation that I was using before. I guess I didn't have my dimensions over here. So these are the dimensions of the spaces that realize these groups. So there's only a unique one from this, a unique one from that, a unique and a unique. So what happens in characteristic 2? Well, the general cubic surface still doesn't have any automorphisms. You still have Eckert points. I talked about these yesterday. Okay. And then things become very different looking. You have an audit, so you have 2 to the 4 acting. Okay. And you also have S3 as normal. Okay. You also have the ordinary cyclic cubic surface. And yeah.
Can I ask about the
Sure.
Eckert point? So to have a evolutional straight to an Eckert point, you have to be able to do one of the two things. Either you write it down in
Yes.
local coordinates and multiply by -1.
Yes.
So, which is not the case, which is not possible here,
Right.
I guess. Or you just take version from the point and take a double cover
Yes.
and take a blind version. But to do this, you need to be sure that it is at least separate double cover.
Right.
Is this the case?
So it is. So I know because of looking at the equations that you can realize these as. So you just look at it rather than multiplying by -1. You take a Jordan canonical form with 1 2x2 block, with eigenvalues 1 along the diagonal, and then you just work out what the cubic surface that has to support this has, and you realize that they exist. And that if you look at, there's a corresponding fixed point, or not fixed. There's a special point that you can associate to this Jordan canonical form, and you look at the general form and you realize that that's the same. So it's I don't know offhand if the projection argument is the same. I imagine it probably is. Yeah, so this is the story in characteristic 2. So far things are looking along sort of this path. Things are looking much the same, and then there's 2 other groups. So what happens is a lot of these automorphisms still exist, but the surfaces that support them end up kind of coming together. And then there is only sort of one special cubic surface in characteristic 2 that has a very large automorphism group. Maybe I'll start with this one. This is PSU 44, which I'll explain what that is in a moment. So maybe I want to contrast what's happening. So before I explain these, I want to point out what the analogs are. So this, in characteristic not 2, okay, you can think about this family sort of has just a ton of, it has additional automorphisms. Okay, so you should think about this one as being sort of specializing to this. This you should think of exactly as analogous to this, the cyclic cubic surface. This guy here contains all of these groups. So it's like all these 3 families, which are separate in other characteristics, all happen to be the same family in characteristic 2. So, and more precisely what I mean is that if you look at these subgroups as conjugacy, the conjugacy classes of these subgroups in the wild group, okay, that this group contains all of those groups if you view it as a subgroup of the wild group. Okay. And this last group, this group is very large, and you should think about it as being this, and this, and there is no automorphism of order 8 in characteristic 2 for a cubic surface, which you can check just by trying to write down in Jordan form and realizing that they don't exist. Okay. So what is this PSU4 coming from? Well, it's just the Fermat cubic. So you have this automorphism, you have this cubic surface, okay? It's smooth in characteristic 2, okay? And then you ask yourself, okay, in other characteristics you can multiply by roots of unity, okay? And you can permute the variables and that's it. Okay? However, in characteristic 2, you have more automorphisms, and the best way to see them is the following. So instead you generalize a little bit, and you say, okay, consider a sesquilinear form, Okay, so I'll write down what the form. I'll write down what. Sorry, I should use a y here. I'll write down what the form is, and then we'll see how this is the same. So you have a sum. These are vectors of dimension 4, and you define this form in the following way. Right, so it's like an ordinary inner product. Okay, except rather than taking complex conjugation, you're taking the Frobenius. So f of x squared is equal, or f of x is equal to x squared. Okay, over f4. Okay, this is a Hermitian form if you evaluate it on itself. So this guy here, which I'll call the actually, what do I call this form? I've already used capital F. Call this capital G. So G, you can think of as a form as being just evaluating this Hermitian form on a vector with itself. And then you realize that the automorphisms of this are just the automorphisms of a Hermitian form, which is by definition this, the projective unitary group. So the automorphisms of the Fermat cubic.
Why is it 4?
So PSU. So maybe I'll tell you what this means. So you should. Another way of thinking about this is F2 squared. If you need the Frobenius to actually have it be interesting from a unitary standpoint, right? So if the unitary group, despite the fact that it's a real group, you're really thinking about it as being embedded in the complex numbers, so you can make sense of what complex conjugation does. So here, you're thinking about this as sort of being embedded in the projective general linear group in F4, except it's not defined over F4, it's sort of defined over F2, and then because you have the Frobenius acting. Does that make sense? So the order of this group is very large. Yes? Sorry? Yeah, semilinear, or sesquilinear. This is a sesquilinear form, symmetric sesquilinear form. And then when you evaluate it on itself, it's what's called a Hermitian form. So the order of this guy is huge. And it's well known and it's simple. And this is 25,960, which you should recognize is exactly half of 51,840. So you realize almost the entire Weil group with this one special surface that happens to be the Fermat.
Can I ask a question? So
Yes.
These are full groups.
They're sorry?
So is it possible to give a little bit of an idea of how you argue that these are the only ones, or these?
Yeah, so that's I'm glossing over that deliberately. So why do you know that these are the only ones? The reason I know that these are the only ones is that I did what Hosso did with the computer program and just enumerated all of them. So if you don't like that, you should think of what I'm doing as giving you examples, and we're hoping to justify it using better techniques than we promise it's true. Which is unfortunately what Cohen and Wales do in their paper. They say, here's a bunch of things, we've checked it, it's true, believe us, and you have to cross your fingers. Yes?
So that if it was 0, then your first answer won't be.
Right, so there's other people have been, so if you don't like the computer proof, then Dolgachev and Askovsky work it out in their paper on the Pomona group, for example. Or you can look at Segre's papers or Cantor and Riemann's papers and account for the errors.
And do you have to start all over again, or can you use characteristic 0? Because you're comparing it to characteristic 0.
Yeah, so in a sense, you do have to start all over again, but you don't really in the sense that you already have some candidates for what the automorphism should be. But you need some way of establishing that there aren't further automorphisms. So why aren't there further automorphisms in characteristic 0 in these cases? And the answer is that you're taking a Hessian and you're looking at the singular points and you say, aha, where did the singular points go? This restricts what the automorphism group can be. In characteristic 2, this thing disappears and you don't have that control. So, and it's very subtle. So if you're not careful, so one of the things that's not obvious at all is if you write down the Clebsch diagonal cubic, okay, then you get exactly the same automorphism group as this thing. And the reason is that with the change of coordinates, you can make it look like this. It's not at all obvious unless you sort of know this in your names. So yeah, so it's tricky to establish that these are all the automorphisms that actually exist. Right, so this is the big one. So what is interesting is that the these are basically exactly the same as the characteristic 0 case. There's nothing kind of funny going on in here. This is exactly the cyclic surfaces with the exact same picture, except when the sort of the J invariant becomes 0, again you end up with this Fermat as opposed to a separate case. So you can really think of this guy as encompassing all three of these cases. They all come together in characteristic 2. Okay, so, and then the last thing I wanted to say about characteristic 2 cubic surfaces is I want to point out why these groups are so big. So if you recall what I talked about on the second lecture on Monday, happened to be there, I told you what the automorphism groups of Del-Pezzo surfaces of degree 4 were in characteristic 2. So you have Del-Pezzo surfaces of degree 4, then you have a two-dimensional family whose automorphism group is 2 to the 4. You got a two-dimensional family whose automorphism group is 2 to the 4 semi-direct product 2 squared, and you had sorry, this is a one-dimensional family. And you had a zero-dimensional family that was 2 to the 4 semi-direct product, the alternating group on 5 letters. And I also told you that in characteristic 2, you have a canonical point on the Del-Pezzo surface of degree 4. So if you blow it up, it turns out it's not on any of the exceptional divisors. If you blow it up, you get a cubic surface. And so you see that all of these groups actually embed into the automorphism groups of the cubic surfaces. So this group, it turns out, is exactly the same. Here, you have an additional element of order 3, and it turns out that these cubic surfaces have a canonical Eckert point. And that canonical Eckert point, if you permute the 3 lines going through that Eckert point, that's where this additional element of order 3 comes from.
What does canonical mean in this case?
Canonical means that if you give me this, if you give me the expression for this cubic surface, then I can do something to this and say, here is the point. It's precisely, in fact, the center of this group is an involution. You can take the Eckert point corresponding to that involution. So those always have a canonical point, which is closely related to the automorphism group.
The center of which group?
The center of its automorphism group. So you take, I mean, it depends on how you want to define it. If you give me a particular cubic surface that happens to have this automorphism group, I can determine that it has that automorphism group, and I can tell you precisely what the canonical point is using some messing around with equations. Or an abstract way of seeing this is if you work out exactly what the structure of this group is, it has a center of order 2, which is a reflection, and its corresponding Eckert point is the canonical Eckert. And then you realize that any element of order 3 is going to permute the 3 lines going through that. Right, so that's the story for cubic surfaces in characteristic 2.
Sorry,
yeah.
I'm confused. So you used to have a canonical point on the Pezzo degree 4, then
Yeah.
you blew it up.
Yes.
And still you have another canonical point on the cubic,
Yeah.
which is somewhere aside.
Yeah. So how do they relate? That's a good question. But it's not for every. So I don't.
No, I mean in case 1.
In this case, yeah. Oh. You might. So yeah, that's a good question. You might be able to see it on the Del-Pezzo surface of degree 4. But I don't know offhand. So that's a good question.
Is it on the exceptional point? The second point.
The second point, yes, it is, because it ends up being. Oh.
Yeah, but then you have P1 and action of something.
I don't follow.
So the question is the right-hand side canonical point over the left-hand side canonical point?
Yeah. I'm not sure if they. I'm not sure if when you blow down you get the. I'm not sure if it's on the exceptional divisor of the thing you're blowing up. I don't think it is because you have this group automorphism group of order 3 which mixes the 3 curves up. So yeah, I never thought about that before. It's a good question. I suspect that if you look at what the automorphism groups of this thing has to be, then you should see from how this acts that there's a point downstairs. It's a good question. I hadn't thought of it. So yes, I think that you probably can see the point downstairs as well. But in this case, you no longer have this canonical point because there's the canonical point sort of exists, except there's many of them now because you have even more automorphisms. So anyway, so yeah. Any other questions about this? I'm going to change topics completely now. So this is cubic surfaces. This was where I wanted to end yesterday. So we know what all the automorphism groups of cubic surfaces look like. Cool. All right, so Okay, so in the remaining time, I want to point out what, I guess, some things about what happens with automorphism groups on other Del Pezzo surfaces, finishing with some observations about Del Pezzo surfaces of degree 2 and more. So let's talk about automorphisms of other Del Pezzos. And mainly for the sake of completeness. So let's start with degree D greater than, well, degree D. So we've already done 4 and 3. Those were the previous, my previous, excuse me, 2 talks. So what else do you get? So for 9, you just have P2. So your G just has to sit inside the automorphism group of PSO3, whatever your field is, algebraic. Oh, I should PGL3, I suppose. Okay. So this is maybe not so interesting, except there's the observation that over any characteristic not equal to 0, there are infinitely many non-abelian simple groups. For sort of a silly reason, namely that you can write down PGL3 FQ, where Q is any power of the base characteristic. So this is very bizarre.
Yes.
Sorry? Yes, sorry, if you want them to be simple, you want it to be PSL2.
And they're all embedded on PGL.
And they all act on P2. I mean, they embedded sort of the obvious way. So this is in contrast to in characteristic 0, the non-abelian simple groups are very restricted. You only have the alternating group of order 5, of order 6, and you have PSL2F7. So you only have 3 characteristic 0. You have infinitely many non-abelian simple groups in other characteristics. So even in characteristic, you know, some 5-digit prime, you still have lots and lots and lots of simple groups, which is bizarre. Other than that, I mean, it's completely just representation theory to figure out what those automorphisms are, so I'm not going to do that. For completeness, I want to mention quickly what happens for some of the other surfaces. So for a Del Pezzo surface of order 8, there's 2 cases here. Either X is isomorphic to a product of projective lines, this we saw previously, or it's just one point blown up. But if you just blow up one point, then that's not minimal, and so you end up with subgroups of PGL3. So this just has all its automorphisms sit inside 2 copies of PGL2, acting on each of these projections. And then you also have a semi-direct product with an automorphism of order 2 that just swaps them. And that's the entire automorphism group, so every group, possible group sits inside there. D equals 7, again, is not interesting because you can always blow down something, and so you always end up back in P2. So D equals 6 is the only other, is the next interesting case. And again, we fully understand what the automorphism group of X looks like in this case. It's simply, it's a 2-dimensional torus, semi-direct product S3 cross S2. So, and I just want to remind you that in a Del Pezzo surface of degree 6, after you've blown up 3 points, you end up with this hexagon of exceptional curves. This group here is precisely the group that acts on the hexagon.
So when you're saying you skip stuff because it's not minimal and you can blow it down, you're working over algebraic closure. You mean you can blow it down
equivariantly? Yeah. So there's no additional automorphisms that we haven't already seen there. So they're sort of uninteresting. Yeah. Yeah, we can blow them down equivariantly. Yes, that's a good point. So here, if you, for example, if you have the standard quadratic transformation acting on the hexagon, then you can't blow it down equivariantly, and you get new automorphisms. But they're not particularly, well, it's kind of dry to figure out what they are. They're not very spectacular. And last, before we get to sort of some more interesting cases, you also have degree 5, and this is an interesting case. Here you get the symmetric group of order 5. This is the only case where you get the entire wild group acting on a representative surface, there's only one such surface. Okay? And one way of seeing this is the del Pezzo surface of degree 5. I'm just going to say this aloud because if you don't know what I'm talking about, it's not going to be helpful at all. It's isomorphic to the moduli space of n-marked points on a stable curve of genus 0. And so what your automorphism group is doing is you're taking these 5 marked points and you're just moving them around. So you're changing the labeling. This is where your automorphisms of the del Pezzo surface come from.
Sorry to interrupt you again.
Yep.
In the case D equals 6, you had the Y group of E. Is it a 6 or a 3?
Yes, thank you. It's a 3. So, yeah, you've blown up 3 points. So we define this to be the wild group of E3. Yeah, thank you. So, right, so this is, you can see right away that this is the kernel of the map to the wild group is not interesting. Yes?
E3 equals A1.
A1 cross E2.
It's A1 cross A2, or plus A2. So, I mean, people don't usually talk about root systems when you're talking about the Pezzo surfaces of such high degree because it's pretty easy to think about them in root ways. Okay, so now we actually get to say some interesting things about the Pezzo surfaces of degree 2 and 1. And I don't know the entire classification. I'm only going to make some interesting observations. So let's talk about degree 2. So in general, I'm going to remind you, I'm using different names for my coordinates, but you can always write down a Pezzo surface of degree 2 in the following form. So you have w squared plus some quadratic polynomial in 3 variables times w plus f, which is a degree 4 polynomial. So this has degree 2, this has degree 4. And where is this embedded? This is embedded in the projective space P2, 1, 1, 1. So W has degree 2, X, Y, and Z have degree 1. Okay, so I think an observation that's already been made is that if the characteristic is not 2, completing the square is something that you can do to this equation. And you end up with the following. So when the characteristic is not 2, you can, there's a change of coordinates. It's actually not even that bad, but I won't bother to write it down. And you can write it down as w squared is equal to a quartic. Maybe I should write an f prime because it's different than the previous one. And then there's an obvious automorphism that you can see right away, regardless of what that quartic is. Namely, you can take w to minus w. So there's an automorphism that acts trivially on x, y, z and takes w to minus w. This is an important enough involution that it has a name. It's called the Geisser involution. And all that it is the deck transformation of the double cover of P2. Okay. And if you think about it for a little while, then you realize that aside from this, you have this Geisser involution, and then you have whatever the automorphisms of this plane quartic are. Right? So the automorphisms of a del Pezzo surface of degree 2, as long as the characteristic is not 2, is simply this Geisser involution direct product with the automorphisms of B, where B is just the branch curve. It's the solutions to f of f equals 0 sitting inside P2. So when the characteristic is not 2, you can completely reduce the automorphisms of a del Pezzo surface of degree 2 to just the automorphisms of a plane quark. So maybe I'll just quickly mention one interesting example, not in character, that gives you a sense that there are some interesting groups that show up. We don't need the cubic surfaces anymore. All right, so I take a very specific example, say w squared plus x to the 4 plus y to the 4 plus z to the 4. So this is often called the Fermat del Pezzo surface because it's the same, whenever you have a sum of powers, you always call it the Fermat blah. This power, of course, is different. Anyway, this is often called the Fermat. And so what's the automorphism group of this guy? Well, we already know that this involution is there, so I won't bother to list that. the automorphisms of this, for exactly the same reason as the description of the automorphisms of the Fermat cubic, okay, this is just z mod 4z squared, so you're just multiplying by fourth roots of unity, semi-direct product S3, where S3 is permuting the 3, but this only applies in characteristic not 2 or 3. 2 is bad because this thing is clearly singular. In fact, it's not even reduced. 3 is bad, not because it's not singular, but because there's more automorphisms. And in fact, by exactly the same trick as I used for the Fermat and characteristic 2, okay, this is the same as like x cubed times x, y cubed times y, z cubed times z. So again, by the same argument, you realize the automorphisms of this guy are PSU3 F9 in characteristic 3. So you again have this sort of large automorphism group, and this is a simple group, and it has order 6048. So it's very large. So the reason I thought it was nice to mention this is you may know about the, I want to say is it the Hurwitz bound? No, it's the, there's a bound on the size of the automorphism group of a curve, a plane curve. Yeah, it's the Hurwitz bound, right? Which is 84G minus 1. So that only applies in characteristic 0, and this is one of the first examples of a curve that violates this bound. So it's interesting. It's not really about del Pezzo surfaces, it's more a fact about curves, but I thought it was worth mentioning because it's interesting. So this violates the Hurwitz bound. So this shows you that the Hurwitz bound only applies in characteristic, well, not 3. You can do similar things for larger.
Is it the largest?
That's a good question. I suspect it probably is, but I don't know.
Do you have some other?
Sorry?
Do you have some weaker bond for?
I don't know offhand.
Yes, there is a linear bound in characteristic. I mean, it's not a constant, but it's a constant times g minus 1.
Oh, it's just a very large constant.
Yeah.
I didn't know that. Yeah.
But it doesn't depend on computers. The constant.
Does the
I don't think so. No.
Can you just take? Well, can you take?
Let me not say anything. Not
Yeah,
before.
it depends on the genus. Because it depends on the...
Yeah, it's going to definitely going to depend on the genus. Yeah. All right. So yeah. So you see that. So in a sense, analyzing del Pezzo surfaces of degree 2 for their automorphisms in characteristic not 2, you're essentially just going to have to figure out what the automorphisms of plane cortex are, which I don't know if somebody has worked out in their entirety, but that's the whole game. So you've reduced it to curves essentially. So what happens in characteristic 2?
Sorry,
Yes.
but you also can have, you use the curve because you take the canonical double cover and then the branch curve.
Right.
And can have the canonical double cover non-separable?
Not in characteristic not 2.
Yeah, sure, just a trick.
Oh, in characteristic 2, no, you can't. So again, so this comes up to the thing that this was mentioned, I think, in the very first talks on Monday. Not my talk, but the one afterwards. It's not obvious, but the answer is that no, it's always a separate.
Yeah, because it is very well to weighted projective space in this way. But now you have directly check. Once you have this embedding and your surface is smooth, then by direct.
But that's it. So you have this embedding, like we say, yes. But
Yes, yeah.
from my part, you don't even see the double cover. Yeah.
Yeah, but it's not possible. It's similar.
Yeah. So the
It's
point is that
non-reduced.
yeah.
So in characteristic 2, you should have.
Yeah. If this is 0, it's going to be an inseparable cover, but it's also just not going to be smooth. And it's not obvious that, I mean, for any particular example, you can just take the partials and check this. But you have to, I mean, I don't know a very quick argument that it's always singular. One thing I could say is that the geyser involution sits inside the while group. And so if it was an inseparable action, then it would mean that your while group, the group acting on the Picard group, was not a constant group scheme, which is nonsense, because it's just a lattice. And so in some sense, because the Geyser involution actually has to be a real legitimate automorphism and not some sort of weird group scheme thing that you wouldn't expect to find in itself. So that's maybe another way of thinking about it. I'm not sure if that you can turn that to a proof or not.
And that's also hold for degree 1. You also have double cover pair. So
Yeah, you have a similar thing that happens. I'm going to talk about that. Yeah. So, but yeah, let me just mention in characteristic 2, yeah, so that's what we just said. In characteristic 2, this Q has to be non-zero. Or else it's singular. So in characteristic 2, Q must be non-zero, and you can't get rid of it. And the simple reason is because, well, if you try to complete the square, you have to divide by 2. And there's a very, very elementary reason why you kind of can't get rid of this. So it has to be non-zero, at least even if you're given it, you can't get rid of it. And also, even if you start with it being 0, it's still a problem. Otherwise, it's singular. But you still have a Geyser involution. So the Geyser now acts as W maps to W plus Q X, Y, Z. And you can check just plugging into the equation. It's a pretty easy calculation that this preserves the form. So so now we've seen sort of an interesting observation that recall that a cubic surface does not have any automorphisms in general. So every Del Pezzo surface has an automorphism over 2. Of degree 2 has an automorphism over 2. And so this completely breaks the correspondence between quartic curves and Del Pezzo surfaces at degree 2. So I wanted to give you sort of a relatively explicit example of this type of thing. So, so there's something called the Klein quartic curve. This realizes the Hurwitz bound in characteristic 0. So this is called the Klein quartic. So and its formula, well, this is the double cover over the Klein quartic. So this, let me just write down the actual curve. So this is just x cubed y plus y cubed z plus z cubed x equals 0. Okay. So this is a curve. I'll call it B because it's suggestive of a branch curve. And the automorphism group of B is the simple group of order 168. When, ironically, the characteristic is different from 2 or 7. So in characteristic 7, this is actually, well, you can't, this is not the expression for the curve. There is a quartic curve that carries this automorphism group. However, it's actually a doubled conic in characteristic 7. So, and it has a different formula. But this is the formula in characteristic 2. Sorry, what do I want to say? No, sorry, this is just bad in characteristic 7. Sorry, 7 is the only bad one. So the curve itself is fine in characteristic 7. But here's the problem. So in characteristic 2, there's no PSL27 invariant quadrant. So if you look at this equation in characteristic 2, quadrant.
We need
Quadrant. So you can find your F, but you can't find a Q.
Yeah,
So
in
characteristic 2.
Different from 2, there's no quadrant as well, I guess.
No, so, well,
But
there could be. I don't know offhand. Yeah, we don't care. Is sort of the answer. As long as that's an irreducible curve, it's smooth, we're fine. And it is in characteristic 2. But in order to make it a Del Pezzo surface, you actually need to find the quadrant. And so, despite the fact that you have this beautiful curve that has this nice structure, you don't have an analogous Del Pezzo surface of degree 2. And in fact, this shows you that you can't realize this group in characteristic 2, despite the fact that we have this beautiful quadrant. And so the correspondence breaks down relatively completely. So you really need to look at this. You really need to look at the conic, and not just the conic and the chord. You can't just look at the chordic anymore. You have to worry about the conic. So it's a very different.
So the list is expected to be smaller, right?
Yeah. Well, given what I've seen about the cubic surfaces, I expect it to be smaller. Yeah. However, it's tricky. So it's not just automorphisms of conics. It's like automorphisms of conics plus some additional information that depends on the chord you pick. So it's just gonna have a very different flavor. Yeah.
I'm a little bit confused.
Yes.
Why does the quadrant also need to be fixed? Because you can also maybe do something with a W, right?
Yeah. So So it's worth pointing out that you can't. So you can show that
in other characteristics, if you have one where Q is 0, you can shift it so that there is a Q again, and then you do.
Yeah. Then the only thing that you can really do aside from changing the actual equation is something that's going to end up being the Geisser evolution. If you mess with W, the only thing you can do that's an automorphism, as opposed to just changing the actual equation, is the Geisser evolution. So it's always a direct product, so you can mess with W and the curve sort of separately. And this is true in characteristic 2. This is the only thing that you can do non-trivially to W that keeps this equation fixed. You can change the equation. I mean, this is exactly how you get rid of Q in characteristic 0. But if you want to keep the equation fixed, that's the only way to do it. And I mean, if you write this down in other characteristics, you can write down an analogous Geisser evolution. It's just going to be more complicated than multiplying by -1.
It's exactly that, except with -1.
Yeah. There's just well, I mean, it's just you're just looking at a quadratic extension, and you're saying what is the Galois automorphism of the corresponding field or algebra. That's all. Okay, so how much time? I am already out of time. So I won't say anything about the del Pezzo surfaces of degree 1, aside from the fact that they are an example of an elliptic fibration. And so you can look at the fibers of a del Pezzo surface of degree 1, and you get something analogous to the Geisser evolution corresponds to the group automorphism of each of the fibers of the elliptic curves. And sometimes you get additional automorphisms of the fiber as well, which are all the same except in characteristic 2, where you get a much larger group. It's just kind of in some cases, which shows up. And because I'm over time, I should probably stop there. Thank you.
So any questions?
So,
Yes.
just want to rectify what I said earlier. There is no linear bound.
Oh, there is no linear bound.
Characteristic, and I mean, there's several infinite families of examples. For example, you can take x to the qy plus y to the qz plus z to the qx equals 0.
Yes.
And incharacteristic p divided q, of course.
Yes.
And that will have some unitary group of fq as automorphisms, like
right.
the group fixing this unitary form. So that will have an automorphism group of order at least qq, it's a three-dimensional group, but the genus is only q squared, so.
So at least there's a linear bound where the constant depends on the characteristic in some real way. A bound linear in the genus.
Well, that's not clear, but certainly there is no universal linear bounds.
Yes.
Yeah, but the bound is non-linear in the characteristic. In the not characteristic, in the number of elements.
It goes diagonal, right? Both the genus and the characteristic vary. Well, no, I can.
Yeah, I see. But
certainly there is no universal linear bound. That's.
So, in del Pezzo degree 1, do you really have always elliptic fibration?
Yeah, you do. So you don't get these quasi-elliptic fibrations. And I don't really have a good answer aside from the fact that there's a reference in Dogachev and Kosek's book on Enrique surfaces. I can find you the specific reference. But I mean, I know that this is true from actually working out, explicitly looking at the equations and realizing that if you...
So what you call equation, you can realize it, right? From the equation.
Yeah, by looking at the equations and trying to, and you say, what makes it singular? You find it, or sorry, can I make this a cuspidal cubic? And you realize that forces it to be singular. But there's a more high-powered reason, but I don't know a good explanation of that.
okay. Also,
yeah.
Question: what's the most, so to say, weird group in the degree 1?
Degree 1. Well, I don't know the full automorphism. I don't know the full classification yet. But what I was going to say is that so in characteristic 2, an elliptic curve can be supersingular and have. And when I say elliptic curve, I really mean the point is fixed. So the group automorphisms can be of order 24. in characteristic 2. There exist Pezzo surfaces of degree 1 whose fibers realize that entire automorphism. So the fiber in other characteristics is only of order 2 or 6, and in characteristic 2 you get this monster fiber of, that has automorphisms of order 24.
It's a single fiber, not every fiber.
No, general fiber.
General fiber.
General fiber has this full gigantic automorphism.
But at least you don't have some huge simple groups already.
No, I mean, well, you can't in the fiber because elliptic curves are a little bit more rigid that way. But and then on the base, which is a Q1, you still have like equations that have fixed degree, and so you end up having the groups have to fix a certain number of, they have to permute 6 points and permute 4 points or 3 points depending on which guys you have there. And so there's significant reductions on the sizes of these groups. So you don't have this kind of thing. Maybe happens, but it's not nearly as bad. You can sort of bound it a priori without actually getting your hands here. Yeah.
Let's thank again. Let's resume in 5 minutes.